last lecture we were talking about catalyst preparation and the various physical process parameters which may affect the properties of the catalyst, because those steps are very crucial in terms of the preparation or developing a definite structure in a catalyst or crystal size. So, if you look at a new catalyst development where a lot of R&D is being done as of today and need to be done. So, this can be for the new product. So, a variety of new process in terms of the green chemistry concept, as I said last time also. So, this can be now there is a need in terms of the from green process or new kind of raw materials and transform into product. So, lot of new catalyst and need to be developed to develop a new product. It can be a different raw material. Selectivity is one of the important issue even for the existing process. So, higher selectivity is desired, as I discussed before. Green process, so clean environment, say just as an example carbon dioxide sequestration, everybody is talking in clean coal technology CCT, right. So, new techniques are to be developed for utilizing the coal, a large amount of biomass coal which may be available and that can be used as a source of energy, right. So, that can be converted into liquid, right, or into hydrogen CTH, but the important thing is that a novel catalyst which should reduce the carbon dioxide into the environment, right, sulfur dioxide into the environment. So, this is very important in terms of the green catalysis or green catalytic process. And then more efficient technology, the existing process may not be efficient. As an example, just as I said, for fertilizer industry hydrogen production process where the nickel on alumina catalyst is used, right, but since the mass transfer is the controlling step. So, effectiveness factor is very low, 0.001 of that order. So, how to improve the catalyst performance? So, ruthenium may be one of the active material for the conversion, right, of naphtha to hydrogen or natural gas to hydrogen. So, depends on the process and new application. So, these are the trends in terms of the catalyst development and which is the innovation need to be done. If you look at the characterization of the catalyst or a physicochemical properties of the catalyst which are generally produced or developed during the catalyst preparation. So, this is also very important issue that bulk density, the density of the pellet, density of the particle, density of the powdered material, right, and when you have made a tablet from that, then what is the density. So, different kind of density, solid material, apparent bulk density, right, and when you put it in the bed depending upon the shape and size. So, the bed density. So, different kind of density. So, the bulk density is very important in that case when you look at the catalytic property, right, in terms of the catalyst depending upon the pressure which you have applied when you make the tablet, right. Surface area, I have said that the most of the time rate of reaction depends on the surface area and a larger surface area may be recommended, right. So, that is very important and depending upon the pore volume, pore size distribution, you will have a definite pore structure which is related to the surface area of the catalyst. So, this is important. Just for example, if you take silica alumina catalyst, the surface area may vary from 200 to 500 meter square per gram, right. Same thing activated carbon may have surface area of 100 meter square per gram or also 1000 meter square per gram depending upon how the porous structure is developed, because the porosity or porous structure of the catalyst is very important if you look at the internal surface area of the catalyst. Same thing for the pore volume also. So, you can have a highly porous material, right, with low mechanical strength or a less porous material with high mechanical strength. So, you have to tune them, right, in terms of the properties and the strength of the catalyst. So, the pore volume may vary from 0.2 to 0.7 or even higher. So, everybody looks for a larger pore volume or larger porosity of the bed, right, catalyst rather not the bed. So, in order to get a definite catalytic reaction inside the porous structure of the catalyst. So, as I said earlier that the calcination or sintering, right. So, that becomes a crucial step, because when you have a nitrate salt, right, or is oxide, that is chloride and converted to the oxide. So, in the presence of ambient air or oxygen, you heat the sample, right, at a certain temperature, right, and maybe the time. So, temperature time is very important and this is what you called calcination and discussed last time, right. So, why do that stuff is very crucial? Because you get a definite porous structure in that, right. So, the formation of new component by solid state reaction. So, this we were discussing yesterday, right. So, there is a diffusion between one species to other, right, or it may be the reverse also, that is a multi component which may be diffusing in one to each other, right. And that time you have a definite concentration in a porous structure, that is one thing. And simultaneously, as I said that nickel oxide and aluminum oxide, they are reacting during that sintering process, and you get a different phase which may be nickel aluminate. So, that is again important, because sometimes the nickel aluminate may be good, right. And similarly, in the calcium aluminate I told 12CO, 7Al2O3 may be a desired phase when you have taken calcium oxide and aluminum oxide and sintered it to certain temperature and time. So, this happens during that formation of new component. So, new phase what I am saying, it is entirely a different chemical composition, and that may have a different activity in terms of adsorption of a gaseous molecule. Then transformation of amorphous regions into the crystalline region. So, as I said, this is the difference between zeolite and a simple clay material, right. So, when you give a proper treatment, say pH is a decisive factor, as I said, right, because nucleate formation, crystal growth. So, a definite crystal may be desired when you prepare the microcrystalline materials, MCM type catalyst, SAPO catalyst, right. So, a definite crystal structure is desired, right. So, same thing in ZSM5 hydrothermal synthesis you do. So, a definite crystal structure is desired, and this is happening during this heat treatment condition. So, very important, and modification of pore structure and the mechanical properties. So, as I said that depending upon temperature and time, there may be a solid reaction and the pores may get narrowed down, right. So, your porosity in one way is decreasing, but mechanical strength may be improving, right. So, you have to tune these two in terms of structure. When the porous structure is highly porous, then strength is poor, right. The particle may crumble during the handling. So, you do not need those kind of pellets, because that these becomes very difficult to handle during a catalytic reaction. So, dispersion, another important factor which you get during the catalyst preparation, right. So, dispersion definition we have already discussed earlier, that the number of metal or active metals which are exposed to the surface, right, and we talk it in terms of the fractional dispersion, right. So, fractional dispersion, when I am saying that available surface atom divided by the total number of atoms which you have taken in the beginning, right, because that is what you get from your ICP studies, right, or some atomic absorption spectroscopy. So, you can determine the total concentration of the metal by extraction. You extract it from the catalyst and then do the absorption in a definite wavelength, right. At a definite wavelength you will get the peak and you can find out the concentration, or ICP can do that job, or SEM EDX can also, although it gives just at a line spectra, but that can also be used if you take the average at different points and then just calculate, just take the average through all the surface or throughout the surface. So, it can be measured, what I mean to say. So, number of surface metal atoms divided by the total number of that metal atom and multiply by 100, you report it percentage dispersion. So, very important phenomenon, and when you have a nanoparticles, it can go to a order of 50%, 60% or even larger, right. But in most of the catalytic reaction, when you prepare it like incipient wetness or wet impregnation method, the dispersion may not be very high, right. But if you even if you get 15% or 20% for those kind of metals, right. So, it is a good number, supposed to be good number, right. So, this is what the important property which you get during the incipient wetness technique or wet impregnation technique, when you look at the precious metal or PGM, what we say platinum group metals, right, noble metals. Physical methods, as I said, to measure this. So, crystallite size you can calculate, right, from X-ray diffraction. So, we will talk on that later. Similarly, scanning electron micrograph, right. So, you can take the pictures, right, of that metal surface and you can see the crystal size, morphology, topology of the surface, right. Similarly, the transmission electron microscopy, right, which also gives the image at high density or high resolution, right. So, that time you can have 3D picture structures also, and you can determine the crystal size very clearly from using this transmission electron microscopy, and the same another high resolution transmission electron microscope, where you can count the particles also, right, and you can compare your dispersion, which can be determined by chemisorption study as well as from this study, right. So, chemical methods are available, which I said is known as chemisorption by using hydrogen, carbon monoxide or hydrogen oxygen titration. So, basically it is a kind of titration, but sophisticated or computational methods are available to evaluate these parameters or dispersion or whatever the surface crystal size or metal crystal size, number of particles. So, all these can be determined in the catalyst. So, this is what I was talking, that what happens or what are the process parameters which may affect the catalytic property is something like that, right. So, rate of drying. So, drying is also important, right, how fast you dry it, at what temperature you are drying, right. So, it is a kind of aging effect. So, you can see here this is a pore of a catalyst, right. So, with time when you have increased the rate, so the metal or solution diffuse into the pore of the catalyst, right. So, at a given rate it may be very high, it may be intermediate or it may be low slow, right. So, this is something like where the uniformly the metal has been deposited throughout the pore surface, right, and this if you do the very high rate of drying. So, what happens, everything just deposits at a local points, something like on a shell, eggshell, right. This is SHELL basically, SHELL, eggshell, right. So, this what I mean to say, that your rate of drying can give you a porous material where the metal may be deposited uniformly like this in the pore. So, this is one pore in a solid like this. There are millions of the pores. So, active metal is deposited like this on the surface, right. The second case may be it is deposited just on the outer periphery, say only this surface is covered, right, at low drying rate, and when it is extreme, everything may go on this side at the pore end, right. So, depending upon that, you can have that the active metal may be deposited just at the outer mouth of the pore, it may deposited at the end of the pore, or it may be uniformly distributed. So, that is depending, or rate of drying is one of the factor which decides this, right. Another thing, that in the same thing in the pellet also, if you have a complete particle or pellet, then also, so we define it egg yolk type, right, where everything is deposited on this side here, right. The second one is the uniform homogeneous. So, similar to this, so homogeneous throughout the pellet, right, and when this is, then it came just everything on the core outer cell, right. So, penetrated outside when the rate is very high. So, if you look at the precious metals, so I told that incipient wetness or wet impregnation method generally we use, right. So, platinum group metals or platinum when you use, so you need a high dispersion. The reason is that they are very expensive, right, the cost is very high. So, only a small concentration of these active metals should be used, and that should be properly utilized, right, without wasting any concentration of that active metal, and this will happen only when you have uniformly distributed it throughout the surface, right. So, this is one impregnation method is preferred for this kind of material, right, platinum material, not the co-precipitation where you take the solutions and then precipitate it. So, most of the part that there may be a possibility that it is not precipitated completely, right, some may left in the solution, right, and when it gets precipitated, it may happen that the every particle is not properly utilized or metal species is properly utilized, because it is in the form of precipitation, right. It may have a clusters of that, right. So, that time, because the concentration is low, so it is advised to use the impregnation technique, right, or especially incipient wetness technique, right. So, activity of these kind of metal will depend on the metal surface area. I am not talking the total surface area, it is the surface area of the metal, active metal, right, and this can also be determined from the chemisorption study, right. So, you can do the hydrogen chemisorption and you can find out the dispersion, and since you know that how many molecules have adsorbed on the surface, say any reactive gas, and whether it is associative or dissociative. So, you can find out that, and then you know that what is the surface area of that one gas molecule, and that can be correlated with the surface area of that matter, because the gas species will chemisorb only on the active metal surface, right, and that fundamental thing you use for determination of the dispersion also, and same thing can be extended to determine the crystallite size, right. So, we will talk on that later. So, metal surface area increase with dispersion. So, when dispersion is high, your surface area of the active metal I am talking. So, because when you define the turnover number, you define the rate per unit area of the active metal, or in other words either you say per unit area of the active metal or in terms of the per unit mass of those active metal, right. So, you multiply by sometime dispersion also. So, that gives you the fraction of the material which is available on the surface, right. This is just an example. If you look at here, the specific surface area, I am talking active metal, not BET surface area here, and this is the crystalline size or crystallite size of the metal, right. So, this is given for a nickel. Just you can see here that as the crystal size increase, surface area decrease, right. So, crystal size is inversely proportional to the surface area, is inversely proportional to the crystallite size. So, that is why we talk nanoparticles. A smaller particle, you have the larger surface area of this order, right. So, this is nickel. For nickel, we have density of roughly, this is the density of the nickel 8,900 kg per meter cube or 8.9 gram per centimeter cube, right. And this example which I have correlated here earlier in terms of the egg cell or egg yolk, the similar thing that the this precious metal or platinum metal distribution profiles has been shown a typical profile. So, these dots represent the active phase and this is representing the support, right, cross, right, or this shaded slant lines are the support portion. So, you can see here that we have talked 4 type of active phase distribution, right. So, uniform type. So, everything is distributed uniformly on the surface, right. So, most of the time we will look at this kind of structure or this type of catalyst, that the complete surface of the support should be utilized. So, dispersion will be better in this case, right. But sometimes when the reaction may have a more of Poisson precursor, right, different type of rate of reactions, very fast, very slow, then we can have the distributions like this also, right. So, this is another one where you can see the egg cell type. So, active metal is just on the outer cell of that cat, right. So, this is something like that. You have a whole support or surface of the solid, and on that the active metal is deposited in this form like this. So, this surface is not being used now, right, only outer surface of the catalyst is being used, and same thing we can correlate with the pore also, as I said, that everything is deposited only here, right. So, rest of the pore is a waste basically, and this is something like when you look at a monoliths, right. So, on that also we just look at a small thickness. So, when the diffusion may be a problem, right, or diffusion resistance is high, then you can look at this kind of deposition, right, because there the diffusion length will be low. So, your resistance for diffusion will be low. So, your rate will be high, right. So, diffusion resistance can be minimized by taking this kind of design, right. Another one which we call is egg white, where you can see it is a kind of ring structure somewhere in between, right, and that is known as direct delta distribution, right. So, when you look at, there are a lot of computational techniques are available in order to identify the position at which or the location where the catalyst concentration should be kept highest, right. So, this kind of distribution may be a direct delta function where the everything is deposited in this zone only in a definite, say, which may be at a distance r and r plus delta r, right, and you call it direct delta function, right. So, this is one kind of distribution and we call it egg white, and this is egg yolk where everything is deposited at the central portion or core of the catalyst, right, at the center, where I said that earlier it is a waste, but now it may be a useful, right, or that is what the rate of drying, as I said, may be 1. the concentration of the acid, right, which may be another, sometimes we call it spacer also, right. So, you give certain concentration of acid, so acid will allow it to penetrate inside, to diffuse inside the surface of the solid. Right. So, the distribution profile for this platinum group metal, if you look at, the optimal dispersion depends on the kinetics of the reaction and mode of catalyst poisoning, right. How the poison precursors, especially when you have a naphtha or hydrocarbon fraction which contains the sulfur, right, and you need to avoid those transformation of those precursors into the catalyst pore, right. So, then you need to look at a definite distribution or what you call optimal distribution of the metal in a catalyst pore or support, and also have a high dispersion, right. So, that is optimal dispersion, which will depend on the kinetics of the reaction, right. Fast reaction, slow reaction, first order reaction, negative order reaction, positive order reaction. So, that is one factor, right. Attrition strength of the catalyst, right. So, when the catalyst strength is poor, then you would not like to deposit it on the outer surface, because what will happen during the attrition like this, right, the outer skin is being crumbled, right. So, particles will fall down from here. So, in that case, if the active metal is deposited on the outer surface, then this will a loss, right, especially when you have a platinum group metal or precious metal, right. So, generally this is some rule of thumb or guideline that XL, if you take XL, I said that something like this distribution, which is a distribution like this on the outer surface, right. So, XL generally favors the reaction with the positive order and fast reaction. So, if the reaction is positive, right, so XL is desired, right. So, the concentration, because positive order reactions, the the rate R A is proportional to the concentration to the power n, right. So, higher the concentration, more will be rate, right. So, you would like to have to complete the reaction in the small zone, because as it diffuse inside, the concentration will decrease down the length, right. So, there the rate will be low, right, because concentration is low. So, for generally positive order reaction, you prefer XL, right. And if you look at other side, egg yolk, which is on the center of the catalyst, so negative order, right, because you need a low concentration, higher will be the rate, right. So, similarly, the other basic I will not say it is not a very important consideration, but sometimes when you design the catalyst, depending upon the type of the reaction and type of the feedstock, we look at a design proper selection of the catalyst, but most of the time we select the uniform catalyst and we try to control the poison or increase the rate by some other design factor. There are several other parameters also by which you can enhance the rate or you can reduce the diffusion resistance. We will talk on that later. So, pore mouth poisoning means the precursor deposits on the outer surface of the, right. So, that time it is advisable to take either egg yolk, right, or egg white, right. So, because you do not want to allow the poison precursor to reach to the platinum surface, right, because your catalyst is very precious and if poison deposits on those surface, your activity becomes 0 or negative, very low, right. So, that is to be avoided, right. So, that time you prefer something like egg white or egg yolk, but not the where the catalyst is deposited on the outer surface egg shell, right. Same thing for the attrition resistance, as I said, when the attrition strength is poor, then do not take XL, right. So, we will prefer the egg white or egg yolk. So, there are several factors for which may affect the dispersion on the platinum metals or platinum group metals. So, the concentration of the platinum metal, right. So, I have taken platinum on alumina as a base, but it can be for ruthenium, it can be for rhodium. So, in general we say platinum group metal, right. So, if you look at this, that the concentration is very important. So, that is why the incipient wetness technique or wet impregnation technique, you take the low concentrations, right, because they are costly, that is one reason. Second thing is that the high dispersion or these metals are highly active. So, a small concentration just like 1% or 0.1% may be effective for the catalytic activity, provided you have designed in such a way that dispersion is high, right. So, it may be 40%, 50%, 60%. So, that means just all those 40% sites are active and available for reaction, that is sufficient for chemical reaction, right. There are large number of atoms which are available in that much mass of the catalyst, right, that you should understand. So, the concentration is very important. So, when the concentration is low, dispersion will be good. So, sometimes you dilute it, right, the fundamental thing of Ostwald dilution law, right. Then presence of competing ions, sometimes you add the third component, right, in order to enhance the either dispersion or in order to enhance the diffusion rate in the surface of a catalyst. So, this competing ions in impregnating solution, that may increase the dispersion. Just like the example, you can have any acid, right, small concentration, very dilute acid, right. You can take HCl also, but only just one drop of that HCl, dilute HCl, and one drop is sufficient for catalytic activity. So, if you look at this, say citric acid is 1, right, and if you take this is the chloroplatinic acid as a platinum precursor, which is to be deposited on alumina, right. So, you are using either impregnation technique, wet impregnation technique or incipient wetness technique. So, a small concentration of this citric acid will push the material inside, but if you have a high concentration, what will happen? Everything will go to the egg yolk type catalyst. So, you have, and if you take a definite, it can give you the egg white also, right, or egg shell when you have a very dilute, or if you do not take, then everything will be deposited uniformly on the surface. So, this is very important, that how to deposit this active metal under the presence or in the presence of some third, which may be called a active material, or which can enhance the dispersion of the metal. So, this is just, if you look at here A, B, C, D, what we have discussed again earlier also, and this is the active phase, which is platinum, right, or taken from H2P2Cl6 chloroplatinic acid. This is your support, which is here like this, all this sided portion is your support. So, this is my platinum here basically inside, right. Here it is in this core zone platinum, here this is uniformly distributed. So, this is the same slides earlier has been discussed. So, that is what I told, that depending upon the concentrations. So, one thing is the rate of drying, that time I was talking just rate of drying, but same thing can be controlled by selecting a proper concentration of the acid, right. So, HCl or citric acid, and you can have. So, if you have high concentration of the HCl or citric acid, then you will get the phase like this or like this. So, everything is going inside, right. So, it will make just a thin layer inside. So, when it is in thin layer, then again your dispersion will go down, right. So, high dispersion may be this case, right, because here it is uniformly distributed, but in this case it is just deposited in a thin layer. So, problem may be that dispersion may be low, right. This may be one consequence of this acid concentration. So, concentration as I discussed earlier, and then this. So, these are important, and this is what is shown here, the increasing concentration of the citric acid. So, as you increase the concentration, so finally you reach to this level. So, this is your active platinum alumina inside, which will happen when you have a high concentration of the citric acid, and this is the case when you have a low concentration of the citric acid, right, and this may be changing like this. If you do not have any concentration, it will give you a kind of uniform distribution, right. So, presence of small concentration of these acid pushes it or increase the rate of diffusion of the solution into the pore of a solid or particle, right. So, you can have a different kind of distributions in the pellet, and these information you can get by transmission electron micrograph, scanning electron micrograph, right. You slice the surface and take the picture, or just by optical microscope also you can take that, right. The another function is the functional group, right. So, that in the beginning we were talking about point of zero charge, when the surface has no charge, right. So, that also becomes very important, because you are adding acid, you are changing the, when you are adjusting the pH. So, you are changing its point of, that is the pH is less than PZC or higher than the PZC. So, you are changing the concentration of the cation positivity or the negativity on the surface, right. So, that is the functional group on substrate surface for binding a precious metal or platinum group metal precursor, that will depend on the point of 0 charge. So, this is important, that first study what is the PZC of that metal. So, point of 0 charge influence the dispersion of platinum metal anions, right, and neutral complexes disperse better on gamma alumina at pH less than 8. This is just an example that the how this PZC is important, right, which will take the concentration of the cations or anions on the surface of the catalyst. So, this I have shown here. If you look at here, the just for an example, for gamma alumina, right, the PZC is between 8 and 9, and if you look at silica, then it is 3, right. So, it means for gamma alumina at 8 or 9, right, there is no charge on the surface when you have taken the pH 8 or 9. Same thing for silica, if pH is 3, the surface has no charge. But if you look at here, for the silica we have taken the different case. So, this is at lower pH, right. So, at lower pH, right, the surface will have a positive charge, right. pH less than PZC, the because here PZC is 3. So, at less than this, the surface will have positive charge like this, all these H positive will come here, will be here, right. And when you have extreme case pH which is higher than PZC, the surface will have a negative charge, right. So, what is the consequence of positive surface? It will take more and more anion, right, and negative it will take more and more cations, right. So, and when it is neutral, then it will have just like the something like OH groups which is attached to the surface. So, when you adjust the pH during the catalyst preparation, it means you are changing the concentration of hydrogen ion or hydroxyl ion, right, on the substrate surface, and accordingly it can take positive metal ions or negative metal ions. So, whether it is alumina or silica, your pH adjustment will be different. So, for different support, the idea is that depending upon the support and their PZC, right, you have to adjust the pH, and simultaneously it will depend on the, when you are doing a co-precipitation technique, then the approach is that at what pH value it gets precipitate, right, that is solubility is another important issue, right. So, here we are talking impregnation technique. So, we are just correlating it with respect to the PZC. So, that is the concentration, right, surface concentrations and pH effect, right, and then crystal size of the substrate, right, that is support which you are taking, what is the size of the. So, sometimes you reduce it to a size of the say 50 micron or say just 100 nanometer, very fine powder, right. The idea is that the one thing is that you are increasing the surface area of those particles, right, because small, and second thing that the particles when you have a smaller, they can bind, because see the particles property change when you change the particle size, right, and when you go to a nano level. So, especially when you look at that monoliths, and on that monolith when you deposit a kind of alumina powder, say it is not easy to just deposit it on the surface or a substrate when the particles are larger in size, right, but when the particles are smaller they can easily stick to the surface. So, these, that is the particle size of the substrate also important. So, when I am saying alumina, ceria, zirconia, right, titania, all these support materials. So, small crystallite size will have large dispersion. So, it means the particle support particle should be considered as small as possible or should be taken as small as possible when you are impregnating it onto that, right, some metal onto that. And same thing that if this is partly reducible oxide support, it also increase the dispersion like platinum on ceria. So, it has the redox property, oxidation reduction ceria on platinum when you have. So, because of that also the dispersion may be higher. So, this is just the depending upon the experimental and the catalyst preparation, right, you have to just check that and then see the effect, that how much ceria concentration is desired, how much platinum concentration is desired, and then look at the conditions and control that, and then you can have these properties which you can develop in a catalyst, right. Then ion exchange method is another one which is generally used for this zeolite catalyst, and where you have a cation and anion exchanger. So, here you can have high dispersion, right. So, platinum group metals, that is the dispersion is increased if you prepare it by ion exchange. So, sometimes we prepare these metals by ion exchange or catalyst by ion exchange method, right. So, for example, just platinum and zeolite if you want to give, so better rather impregnation use the ion exchange. So, you have H positive ion on the zeolite or ammonia, you convert it into ammonium ZSM5 and replace that ammonia of the zeolite by platinum, right. So, platinum, gallium, so these can be impregnated onto the zeolite catalyst by ion exchange procedure, right. But there should be a sufficient ion exchange capacity, right. So, again the time, pH, particle size, these will be crucial. Sintering, so that is what you get during firing of a catalyst. So, calcination, so it leads to a lower dispersion. So, metal surface area and activity drops, right. So, MSC refers to metal surface area, right. So, when you have a calcination conditions, right. So, you have to do it controlled way, because that is the crucial step where you get different phase, but simultaneously since you are heating it to a time course, right, given time, right. So, the particles may come closer, right, a kind of reaction. So, you have made some nanoparticles during your aging or drying step or right co-precipitation step, but when you are given the heat treatment, then the particles may again coalesce or become larger. So, this is the problem, as I said, that for the nanoparticles of platinum group metal. So, when you give the heat treatment, they may agglomerate and reduces the dispersion, right, because the crystal size now increase, right, it grows. So, metal loading, if you have high, then again the same problem, right. So, because larger number of metal concentration on the surface and now more reaction when you have a high temperature condition, right. Temperature, time of stream, water, oxygen, sulfur, chloride, they are also affecting the performance or the crystal size or dispersion when you give the heat treatment. So, this should be avoided. So, a definite temperature is desired, right, not more than certain level, that you have to tune it or check it. Same thing, time on stream, right. Water may be a problem. So, do sufficient aging or drying before calcination, right, and same thing, oxygen environment should be controlled, right. Sulfur, chloride, these should be avoided, right. So, that these are the certain precursors, right, which may affect the performance. So, increase with crystallized size of the support. If crystal size is high, then also your sintering, that is the, if you look at the reaction. So, sintering depends on the crystal size. So, when you have a sintering, then crystal size will increase, right. Increase with hydrophobicity of the support, right. So, support is hydrophobic or hydrophilic. So, again your metal surface and activity, that becomes a crucial factor depending upon the surface, right. So, you have to look at that, the platinum silica, platinum alumina if you have. So, platinum silica sinters more compared to platinum alumina, right. So, if you have platinum on silica, that may not be a good when you have a, because the during the sintering the agglomeration will take place. So, dispersion with platinum silica catalyst, right. Platinum, yeah, this sinters more, so dispersion is less here and dispersion is more in the platinum alumina catalyst, right. Same thing, sometime we add the spacers, right, zirconia in ceria, right, to avoid the sintering phenomena, right, the crystal. So, solid reaction I am saying that is to be avoided, right. So, sintering is to be avoided. Suppressed by binding groups on the surface, hydroxyl, chloride, sulphate, like this what I said. So, that if they are present, so sometimes the chlorination is done, right, during that sintering time, because the dispersion will improve in that case. So, that avoids the sintering phenomena. So, we need to calcine the catalyst, but this sintering is undesired basically, right, because sintering is nothing but the solid agglomeration, right. So, two small crystals comes closer because of high temperature and time and becomes a larger, right. So, surface area of the crystal decrease, dispersion decreases, and these are the parameters which affect the sintering performance, right. So, we try to avoid the sintering. So, it means the temperature should be controlled, time of steam should be controlled, right, water should be avoided, oxygen concentration should be kept low, right, and same thing for sulfur and all these chloride species, right. So, you have to control these poison precursors in the catalyst. So, high purity metals are required when you prepare the catalyst. So, the characterization what we are talking, surface area, pore volume, pore size distribution, all these things can be determined based on simple condensation of any inert gas on the surface of the solid, right. And we discussed physical adsorption and chemical adsorption. So, chemical adsorption means you need a chemical reactive gas, and physical adsorption means any gas which can be adsorbed on the gas surface, right, below its critical temperature. So, if you look at here, the texture and morphology, right, that is the first important property of a catalyst, the texture, how does it look like, right, morphology, spherical, right, or what is the shape of that particle, right, and in depth if you look at how the cracks have been developed inside, right, porous structure has been developed in the catalyst. So, in that case, the first thing is that specific surface area of the catalyst, that is surface area of the catalyst per unit mass of that solid material, right. So, that is to be identified or determined. Then size of the pore, that is important, because you have done all these preparation methods, you are by using those methods you have prepared the catalyst, and now you would like to check the texture property or morphology of that solid material, right. So, that is kind of physical characterization of the catalyst, right. So, surface characterization in terms of the textural properties or morphology of the catalyst, right. So, pore size, pore shape, pore size distribution, right, and pore volume. So, these are the properties of the catalyst which can be determined based on physical adsorption. So, why do you need that? Why do you study this pore size distribution or pore size measurement? The reason is here, right, that it dictates the diffusion process through the material, right, because you know larger pore, the gas methane can diffuse easily, right. Small pore, right, methane may go, but aromatic may not go, or branched compounds may not go. So, if they are difficult to penetrate inside, so it means the diffusion resistance may be a dominating parameter. So, basically in one way you are calculating the transport properties, right, or diffusion coefficient for that gaseous species into the pore, right. But you should know on a priori that what is your pore size, what kind of pores are available in that solid material, and based on that only you can give your theory, right, or postulate your theory, or you can control, suppose you want to minimize the diffusion resistance. So, accordingly you can control it, right. So, there can be the parameters in terms of temperature, in terms of particle size, or in terms of development of the catalyst itself, right. But once the catalyst has already been developed, then it will be the secondary parameters by which you can control it to the certain level. But when you are preparing a catalyst, then on a priori you should know what is your reaction, for what type of reaction you look those catalysts, right, and then depending upon the molecular property of those chemical species, and then you try to develop a definite kind of support. So, that is why the computational method may help you to develop a definite kind of structure, and you try to reach to that type of structure experimentally, right. So, this is what the state of art in catalyst development, and then look at this property. So, in general when you look at a solid material, there can be different type of diffusion phenomenon, right. So, one is known as the molecular diffusion, right. So, molecular diffusion means nothing but the kinetic. So, based on kinetic, molecules are colliding and penetrating its side, right. So, that is one thing. So, there are different correlations by which you can find out the diffusion coefficients, right. And second thing is your Knudsen diffusion, right, and generally this happens in small pores. So, one thing is that the collision is between the molecules and the molecules are moving. The another thing is that since the pores are narrower, the channel is narrower. So, what will happen? The molecule will collide among themselves, but also they will collide with the wall of that, because it is a narrower lane, right, and molecules are moving. So, when the molecules, larger molecules move in a small lane, then the possibility or probability is that the molecule will strike with the wall more, and then they will move, right. So, that is known as a Knudsen diffusion, right. Whereas, the molecules when they are colliding among themselves and moves, that is known as bulk diffusion or molecular diffusion, right. So, bulk of the molecules they are moving because they are colliding among themselves, and second is the molecules are colliding with the wall and then penetrating it. And sometimes generally it is a very rare phenomena, the surface migration, the molecules are adsorbed on the surface and they are migrating because of the temperature phenomenon, right. They leave the surface and move to the other side, right. Surface just like in a reaction on the surface, it is a kind of diffusion on the surface. So, migration of the molecules from surface to surface because of the temperature phenomena, right, or surface property, right. So, this depends on the type of pore here. I am talking this thing for a property of the gas, molecular property of the gas or any reacting molecule which has come to the surface of the solid and planning to react or penetrating inside, and then it will react, transform into a product, right. So, it means the first thing is that understand how these molecules can go into the pore or can they go inside or not, right, because for a chemical reaction the molecule has to go inside a pore of a catalyst. So, the first thing is that depending upon the kinetic diameter of that molecule, depending upon the pore size, you have to take this understanding or phenomenon that which kind of diffusion is dominating. So, molecular diffusion, right, larger pore, generally in the larger pore, right. Knudsen diffusion, a small pore, so diffusion will be difficult. So, but when it will dominate at high pressure, right, or temperature, right. So, again there are some other factors like kinetic diameter, I said radius of the pore is important, right, molecular weight of the gas is important. So, if the molecular weight of the gas is high, right, that is related to the diameter of the molecule. So, diffusion will be slow, right. So, the first one diffusion, you know the kinetic diameter, the molecules are colliding among themselves. So, it will be a function of temperature, more dependent on temperature, less on pressure and like, right. So, there are several phenomena. So, temperature, pressure, everything and the diameter of the molecule. So, Knudsen diffusion, bulk diffusion and surface diffusion, this may happen. So, that is what the first understanding, that can a molecule penetrate, if it penetrates then how, right, because of diffusion. The convective term may be there, but generally that will be very small because you are talking a surface of the solid. So, the velocity becomes 0 and then it is diffusing, right, because of the concentration gradient, right. So, you can see here the activation energy which is required for these kind of pores, right. So, pore is increasing in this side, that is why I said that in larger pore you will have molecular diffusion, the intermediate pores between 10 or 1 to 100 angstrom, Knudsen diffusion is nanometer, 1 to 100 nanometer Knudsen diffusion, and then at very small pore and high temperature surface diffusion, right. This is the activation energy graph. So, again you can see here the pores are increasing in this, pore size is increasing, right. So, pores when they are larger, temperature, the activation energy, it is not a problem, right, because the molecule can go easily, and this is basically a fundamental thing for surface diffusion. That is why I said that temperature phenomena very important, right. When the activation energy is very high, it means it will require higher temperature for diffusion, right. Same fundamental thing, that the higher temperature will favor the transmission or transformation towards the higher activation energy, right. So, suppose you have a multiple reaction as I discussed earlier also, A goes to R and A goes to S. So, depending upon the activation energy E1 and E2, the temperature will show its direction, right. Suppose if I say E1 is greater than E2 and if you increase the temperature, then rate of formation of R will be more compared to S, right. That is what I am saying, that higher temperature favors the reaction of higher activation energy. Same thing here in the diffusion phenomena, the activation energy for surface diffusion is higher compared to the bulk and the kinetic, because I told you diffusion control reactions will have low activation energy. We will discuss that later, but right, rule of thumb, kinetic control reactions will have higher activation energy, right. So, it means this is the fundamental here, that surface diffusion will take place at high temperatures, right, and here this is what the bulk and Knudsen diffusion, which has less effect on temperature, but other properties are very important. Molecular dimension is very important, pressure has a role of course, right. You can see that. So, we just have discussed this slide earlier, that in a pore, when you look at a catalyst geometry or porous structure, there may be a micropore, mesopore and macropore, right. By definition we say the pores less than 2 nanometer is the micropores, 2 and 50. So, between 2 and 50 these are your mesopore, and more than 50 nanometer or sometimes we call it 100 also macropores. So, that is between the particle, and then also shape of the pore, it may be straight cylindrical. So, most of the time we assume the pores as straight cylindrical, right. It may be closed from one ends, it may be open from both ends, right. But even the pores are not straight cylindrical, we take the average pore as a straight cylindrical by considering some non cylindrical parameters. So, we will talk on that later, right. It can be a slit type like this, say alumina mainly lamellar type structure or slit type. It can be ink bottle type like this, right, and it can be a wedge type structures again in the most of the siliceous materials, right, calcium silicates, and they can have either this type or that type structure, right. The selectivity is very important issue when you look at a pore size or pore size distribution. So, this is just an example of zeolite type catalyst if you look at, or any porous structure materials where a material, a reactant species which is straight chain like this, right. So, that is the selectivity term which we are defining. So, this is a straight chain molecule here, right. This can go easily into the pore, right, and crack smaller paraffin and one olefin like this, right, or one small, two smaller molecules. So, it can easily go, but if you have some other molecule which is branched here, right, or something like aromatic, so it cannot go inside the pore of a catalyst. So, it can be a poison precursor also like sulfur species, right, cyclic sulfur compounds, it can be aromatic. So, this cannot go inside. So, this will not go inside, or if it is a poison precursor, it will not damage the catalyst pore. So, that is the meaning of selectivity. So, this is a reactant selectivity we call it, where only one type of reactant or one reactant can go inside, but not the other, right. This can be a product selectivity also, because this is the what we are talking, that the selectivity of the reaction can be affected depending upon the pore structure, right. So, you can see here you have methanol, you have something like a cyclic compound, right, maybe a toluene, benzene, right, and they have gone because it is a larger pore, both are gone inside, and then now here it is a larger arrow compound, which may be a 2-ring compound, or it may be just like orthoxylene, right, metaxylene, paraxylene, whatever. So, these type of species may form, right, but this may come here just like when you have a isoxylene or sorry this isoparaffins formation, right, in some other pores, right, straight chain paraffin may form the isoparaffin, but if aromatic is formed it cannot come out, right, it will remain there. Same thing when you have a coke precursor aromatics, right. So, dehydrogenation of aromatic and you get the product, but simultaneously you get the coke also. So, coke may not come because coke is a polycondensed aromatic hydrocarbon. So, that may be blocked inside, right, or remain inside. So, this is now only this molecule has come out, but this structure cannot come out, right, it remained there inside. So, that is known as product selectivity. So, selectivity of this kind of molecule will be now high. The only thing that your catalyst is being deactivated, right. So, you have to regenerate that or remove that time to time, but otherwise you are getting the whatever the ortho, meta, para type gyrenes or desired component from that. Sometimes it can be restricted transition state selectivity, right. The meaning is that this kind of molecule orientation, because I said orientation of molecule is also equally important. So, this kind of molecule can go inside, right, the pore and then isomerize or converts it into product, but very difficult because the molecule has this kind of transition state which is formed during the reaction, right. So, this and this is the some types of alkylated, if you look at ortho group, right, or meta group or para type. So, para type, but here if you look at the ortho and meta, right, connections are at this and this not at this. So, this structure can come out, but not this one. So, this is that intermediate has formed during the reaction. So, which kind of intermediate product has formed? It is something like A goes to B and B goes to C. Suppose B is a larger molecule, so it will remain inside. So, when you have a reaction like Fischer-Tropsch synthesis, you get a series of the product. So, that is the wax formation. So, that is the problem in the Fischer-Tropsch, that large amount of wax forms and that poisons the catalyst, right. Same thing when you look at the methane conversion to liquid hydrocarbon, you have to look at these kind of, because methane is converting into a larger molecules, right. So, to what extent larger? If coke is forming, it will remain there or it will block there, but if this is kind of structure, a definite kind of pore structure, it will continuously come out, right, but this will block the pore. So, there can be a different kind of selectivity which may be good also, but sometime most of the time they are good, but sometimes they may be a poison precursor and that deactivates the catalyst. So, right now we are talking activity of the catalyst, but this could be the consequence of catalyst deactivation, right, because of the undesired product species formed and it remained inside or deposited on the catalyst surface. So, if you look at the pore size, shape, right, distribution of the pore, they are very important and need to be determined. So, we have several methods by which we can determine the pore size and shape of a catalyst, which are based on physical adsorption technique, right. So, the one of the most important or commonly known is known as mercury porosimeter method, right. The second one is known as nitrogen adsorption desorption method, capillary condensation, that is the phenomenon which is based on capillary condensation, right. And these can give you a wider range of pore size distribution, that is, as I said, micropores, macropores and in between mesopores. So, if you use these two together or combined, then you can find out the complete pore size distribution, right. So, 1 to 10,000 angstrom, 10,000 means large number, right, 10,000 nanometer here. So, it is a very large pore, right. So, these can be used to determine the catalyst property. So, I stop here and we will continue it next time.